We are diving straight into the HunyuanOCR technical report from the Tencent Hunyuan Vision team. This one's a big deal.
It is. It's really about a fundamental shift in how we approach optical character recognition, moving it out of these old, clunky pipelines and into a single, sleek vision language model.
Okay, so for everyone who needs the top-line summary right now, let's do the one-minute rundown.
Let's do it. Okay, so the mission was clear. Build a commercial-grade, open-source VLM that is laser-focused on OCR, and they pulled it off with just 1 billion parameters.
Which is tiny.
It's the whole story. That size means it's actually deployable, it has low latency, and it still manages to beat out much, much larger models like Qwen 3 VL4B.
Yeah.
It's a completely end-to-end architecture. So that whole problem of errors stacking up from one step to the next in systems like Paddle OCR, it's just gone, solved at a fundamental level. And this is the real kicker. They're the first to really show that reinforcement learning, specifically an algorithm called GRPO, can give you huge performance gains on these structured OCR tasks.
So it's not just one model for one task.
Yeah. Not at all. It unifies 5 core tasks. We're talking spotting, parsing, information extraction, VQA, and even translation, all in one framework. And it's not just a lab experiment. It won the small model track at the ICDR 2025 DIMT challenge. So it's validated.
Okay, let's unpack that, because that efficiency to performance claim is where the real commercial value is.
Yeah.
To get why this is such a big leap, we have to start with how things used to be done. The old world of OCR.
Right, the pipeline problem. It's not a new issue. I mean, you look at almost any legacy system, whether it's easy OCR or even some of the bigger enterprise ones, and they're all built on this cascade of different modules.
You have one module for, say, finding the text.
Yep. That's your text detection, finding the bounding boxes. Then you pass that to another module for text recognition, which figures out what's in the boxes. Then maybe another one for layout analysis or parsing tables.
And on paper, that sounds, like a solid modular engineering approach. But the paper is really clear about the downsides. It's complex, it's a nightmare to maintain, and the big one progressive error amplification.
Exactly. That's the pipeline effect in a nutshell. If your detection module messes up in step 1, it misses a word or draws a box a little bit wrong, every single step that comes after it inherits that mistake.
And probably makes it worse.
It almost always makes it worse.
Yeah.
The recognition engine, the parser, they're all working with bad data. Your whole system is only as strong as its weakest, earliest link.
So the VLM approach here is designed to just completely sidestep that problem. One model, one inference pass. But I have to ask, when you try to unify 5 really different tasks like spotting, parsing, VQA, isn't that usually a recipe for being just okay at everything and great at nothing?
That is the core challenge they're tackling. Their argument is that the old OCR expert models were too specialized, too narrow, and the massive general-purpose VLMs are just way too slow and expensive for real commercial use.
So this is the sweet spot.
This is their answer. The end-to-end model learns to optimize for all the outputs at the same time, looking at the original image, not some degraded intermediate step. So you get this huge capability coverage, from spotting text in a video game to pulling subtitles, all run by simple natural language instructions, and all inside that really tight 1 billion parameter budget.
That 1B scale is, I think, the part we have to keep coming back to. It's what makes it practical. It means low latency, high throughput. But how do you actually cram that much OCR power into such a small model? It has to be more than just hooking up a small LLM to a vision encoder.
Oh, absolutely. It's all about how the components work together in a really specialized, really efficient way. There are 3 main pieces to the architecture. First, you've got the native resolution visual encoder, the Hunyuan VT.
Okay, so that's about 0.4 billion parameters based on SIGLIP. But what's the secret sauce there? Why is native resolution so important for OCR? Don't most models just resize everything?
And that's exactly the problem they solve. Think about it. If you take a high-res scan of a contract or a long invoice and you squish it down to a standard 224 by 224 square,
you lose everything.
Yeah.
All the small text, the details, it's just a blur.
You've just destroyed your input data. So their adaptive patching mechanism is the key. It keeps the original aspect ratio and resolution, so the features it sends forward are rich and detailed. For long, text-heavy documents, that's non-negotiable.
Okay, so now you've got these gigantic, high-resolution feature maps coming out of the vision encoder. That must create a token sequence that's just massive. How do you stop that from totally overwhelming the language model?
Right, that's where the second piece comes in, the bridge. It's called the adaptive MLP connector. And its job is to perform what they call spatial dimension adaptive content compression.
Which sounds complicated.
Think of it like a smart filter. It uses a learnable pooling operation, so it's not just blindly chopping down the sequence. It looks at the feature map and figures out which parts are dense with text and which parts are just background. It preserves the important semantic info from the text regions and, well, it discards the fluff. That's what keeps the input to the language model manageable and fast.
And that brings us to the LLM itself, the Hunyuan 0.5b. It's incredibly small for a language model, but it's got to do all this heavy lifting with complex layouts and structured data. What makes it capable of understanding a 2D document?
It's a feature called XD-ROPE. So your standard rotary positional embeddings, ROPE, are usually just one-dimensional. They know the order of tokens in a sequence.
Right.
But XD-ROPE deconstructs that embedding into 4 different subspaces. One for the text itself, but then also ones for height, width, and even time.
Ah, so it can understand spatial relationships.
Precisely. This is what lets a tiny 0.5b model natively understand that this piece of text is above that one, or that this cell belongs in this column of a table. It's a huge deal for parsing complex layouts.
So it's that combination, the native resolution VIT, the smart compression from the MLP connector, and the 2D-aware LLM that lets them deliver on that promise of a high-performance, low-latency 1B model.
Absolutely. And for anyone listening who's actually building these systems, they don't just stop at the theory. They provide a high-performance deployment solution built on VLM. That's a huge signal that this is built for production, for speed, for real-world use.
Right. The architecture gives you the foundation, but a model is nothing without the right training. The paper goes into a lot of detail about their 4-stage pre-training recipe.
Yeah, and it's very methodical. They don't just throw data at it. Stage 1 is just vision language alignment. It's basically teaching the model the ABCs of parsing and recognition using just the VIT and the adapter.
Building up the basics.
Exactly. Then stage 2, they unfreeze everything and do a huge multimodal pre-training, run 300 billion tokens to get that deep understanding of complex things like tables and documents.
And then they address the problem of really long documents.
That's stage 3. They specifically work on extending the context window out to 32,000 tokens. You absolutely need that for processing multi-page PDFs or giant high-res scans. And then finally, stage 4 is supervised fine-tuning with human-annotated data, teaching the model to follow specific instructions.
Which sets it up for the most innovative part of the training process, reinforcement learning. Now, RL is something we usually hear about for, training chatbots or mastering Go. Why does it make sense for OCR?
It's a fantastic question. The reason it works so well here is that OCR tasks, especially things like spotting text and parsing tables, are highly structured. And more importantly, they're verifiable.
There's a right answer.
There is a right answer. Unlike a creative writing task, we know exactly what the text should say and where the bounding box should be. That verifiability lets you design really precise, really smart reward functions that can guide the model way better than a simple loss function can.
So the RL isn't just optimizing for the text, it's optimizing for the structure, for the coordinates, for everything all at once.
That's it. They use an algorithm called GRPO, but the real genius is in how they design the rewards. They split the tasks into 2 groups.
Okay, let's start with the first group, the closed-form tasks like text spotting. They call this reinforcement learning with verifiable rewards, or RLVR. What does that reward function actually look like?
So for spotting, you need 2 things to be right: the location of the text and the content of the text. The reward function is designed to capture both. It's basically calculated as 1 minus the normalized edit distance, so how many characters are wrong. But that score is only maximized if the intersection over union, the IOU, of the bounding boxes is high.
That makes perfect sense. So you could get the text 100% right, but if your bounding box is way off, your reward is low, it forces the model to learn both things together.
It directly attacks that old pipeline problem, but at the metric level. Now for the second group, the more open-ended tasks like translation or VQA, the ground truth there is a bit fuzzier. So they switch to an LLM as a judge approach.
Using another, bigger LLM to grade the output.
Yep. For translation, a scoring LLM gives a soft reward, say from 0 to 5, but they do another clever thing. They apply a debias normalization to that score, which basically stretches out the middle of the range scores from 2 to 4.
Why do that?
Because that's where the subtle improvements happen. It makes the model more sensitive to small gains in fluency or accuracy that a coarser reward signal might just miss.
And did this whole RL phase actually move the needle on performance?
Oh, significantly. The paper is really clear on this. The OCRBench parsing score alone jumped from 92.5 to 94.1. The information extraction tasks improved by over 2 points. It's definitive proof that this kind of targeted RL is a powerful final polishing step, even for a specialized model.
Okay, so from training to actually using the thing, how does one model handle this huge variety of tasks? It's all about the instructions, right? What do those outputs look like for a developer?
They're designed to be machine readable right out of the box. For basic spotting, the model just gives you the text and the coordinates in a clean format, like rough text ref quad by 1y1 by 2y2 quad. It's structured and ready to go. But then for fine-grained parsing, it gets even smarter. You can tell it to parse a mathematical formula, and it will output it as latex. You tell it to parse a table, it gives you clean HTML. It can even take charts and flowcharts and structure them using Mermaid or Markdown.
So you're getting structured, usable data back, not just a wall of text.
Exactly. And it handles full end-to-end document parsing, too. One prompt can tell it to process an entire document, convert the text to Markdown, the tables to HTML, the formulas to latex, all while keeping the correct reading order.
And for information extraction, like from an invoice?
Just as easy. It's instruction-driven. You can literally prompt it. Extract invoice number, total amount, and return in JSON format. It works for over 30 common document types and even video subtitles.
That level of unification is wild.
Yeah.
But okay, the final test is always the benchmarks. Does this little 1B model really hold its own against the big guys in the old legacy systems?
It doesn't just hold its own. In many cases, it blows them away. If you look at general spotting performance, HunyuanOCR scores a 70.92 overall. Now, compare that to a traditional pipeline system like PaddleOCR at 53.38.
Right.
Or even a bigger general VLM like Seed 1.6 Vision at 59.23. The focus of this model gives it a robustness that the others just lack, especially on really hard stuff like artistic text or text in video frames.
And what about parsing? That's where complex layouts really test the architecture.
SOTA performance. It gets the highest overall score on OmniDocBench with a 94.N0, and critically, it also wins on the much harder Wild OmniDocBench dataset, which has real-world distorted images. That shows the RL training and the architecture really pay off. It beats larger competitors, and it even achieves SOTA on multilingual parsing across 14 languages.
Okay, let's hit the high-value commercial stuff. Information extraction, VQA.
Right. Accuracy on common documents is key. They're getting 92.29 on cards, 92.53 on receipts. But the most shocking result to me was video subtitles, 92.87 accuracy.
That sounds high. How does it compare?
Well, a massive model like Qwen3 VL235B, which is hundreds of times larger, scored just 50.74 on that same task. It's a perfect example of how a smaller, hyper-optimized model can just dominate a specific domain.
So is there anywhere that the 1B parameter size is actually a limitation? A clear weakness?
Yes, and the paper is very upfront about it. Translation. Well, the model is actually pretty good at document translation beating models over 4B parameters. The raw generative power of that tiny 0.5B LLM just isn't on par with bigger language models. Its fluency lags behind its incredible detection and parsing abilities.
So if a developer needs top-tier parsing and top-tier translation, what's the recommended approach?
They actually suggest a pretty smart hybrid solution. Use HunyuanOCR for what it's best at, the heavy lifting of visual analysis, detection, and parsing the document structure. Then you can just pipe that perfectly structured output into a dedicated high-accuracy translation model like their own Hunyuan MT7B. You get the best of both worlds.
So to sum it all up, this paper really feels like a proof of concept for a whole new way of building specialized AI. It shows that an end-to-end VLM, if you design the architecture right and use targeted strategies like RL, can deliver SOTA performance in a package that's actually small enough to deploy efficiently.
It's a blueprint for efficient, powerful AI, and their future goals just double down on that. They're focused on making it even faster, more efficient, able to handle multi-page documents, all with the goal of getting this running on edge devices.
Which brings us to a really interesting final question for you, the listener, to think about.
Yeah. We've just seen how incredibly effective reinforcement learning can be for optimizing these highly structured, verifiable tasks like OCR. So the question is, what other computer vision tasks that have always been stuck in these old, clunky pipelines, things like, say, detailed instance segmentation or maybe multi-object tracking, what other areas could get the biggest boost from applying these kinds of ability-adaptive, fine-grained RL strategies today? It really feels like the door is wide open now.